Hello, and welcome back to this video series in which I cover the basic steps needed to build mini simulations. I am focusing on the corona discharge example. In this video, I will explain how to add particles, the particle boundary conditions, and reactions. In VSim, you must specify both the particle and field boundary conditions. In this video, I will show you how to add particle boundary conditions. In the next video, I will go over field boundary conditions. So let's get started by looking at this generic example that we have been setting up. So to add particles, you need to expand this particle dynamics option and right-click on kinetic particles. And then this will allow you to add charged particles, electrons, and neutral particles. So let's add electrons. So again, there will be some default name that's already there for you. You can double click and change it. I can just change this to electrons. You need to establish some nominal background density for that species or for that population. There are different ways to evolve this. It's best just to keep it relativistic. That'll always be correct. You can do different weight settings, so you can do variable weights, constant weights, and managed weights. Managed weights is a very useful option if you're going to be having a lot of reactions and you could lose or gain lots of particles. Managed weights lets you keep the particles per cell within some range. So we're just going to keep this with variable weights. Once you add the electrons, you can do many things with them. And when I show you the corona discharge example, I'll show you more of what you can do. But let's just say we wanted to add some particles initially when the simulation begins. Then we would add a particle loader. So you would right-click on electrons, go to Add Particle Loader, and click on Particle Loader. Now you can see you can have as many particle loaders as you want. So I could specify some population in the lower left quarter and a different population in the upper right if I wanted to. So we're going to get rid of the second one. So under particle loader, again, so the initial density of the population is based on what you put here. So here the default was 1 to the 18 per meter cubed. So we'll leave that number. And this number 1, this relative density here, says that this population will be 1 to the 18th. If I made it 0.5, then the population would be half that. And you can even put in a space-time function here if you wanted, if there was some density that was a initial function of space. You can specify the initial velocity distribution. So if you go up here to space-time function, I could add a new space-time function. We'll call it Maxwellian electrons, M-A-X-E-L. And so V thermal E was the thermal velocity that we defined before. And 0.0 says it has 0 drift. You could put in a drift if you wanted. Now that we've established that, or created that space-time function, then I could give this a Maxwellian by right-clicking here, go to Add Space-Time Function, okay. Now you have to specify where it's going to sit in the domain. And so to do that, you just double-click here. There's only one option, Cartesian 3D slab. And this is where it's going to be initialized in the domain. You can see that population by hiding the geometries. And we'll get rid of the grid, or we'll hide the grid. And there is my initial electron population. You can see that that's it, because when I change the dimensions and where they're initialized, then this changes. I'm going to add a neutral fluid. So right click on fluids, add neutral fluid, and there's my background hydrogen population. You can change that by double clicking here and putting in other species. So N2, for example, and then everything gets pre-populated. Of course, you can also just add a custom species or molecule, but then you'd have to put in the information yourself, like the mass and the ionization energy. Again, you have to specify the volume, and you need to also specify the density. So 1 per meter cubed isn't very many. Often this density, you could put in a parameter in which the density is computed based on the pressure. And that's what I'll show you in the corona discharge example. That's what I did. Now that we have an electron population and a neutral fluid, you can add a reaction. So if I expand the reactions option, and also just remember that all of these options and tabs are there because in the basic settings tab we set it to include particles and also to include reactions. These tabs are not here if you don't go into basic settings and include particles and reactions. Alright, so under the reactions tab, which is under particle dynamics, I can right click here and I can add a collision. So let's add an elastic collision. So this just says that A plus B react to form A plus B. There's no new species, they just bounce off each other with the total energy and momentum conserved. For A, you can double click here and that would just, there's only one species that we put in, but if you put in multiple species, there would be multiple species under the options. And then for B, that would be their fluid. For the cross section, there are lots of options, but let's just do interpolated from 2D data set, and I'll show you that in just a minute. Typically, the cross-section variable is energy, and then you have to go find your cross-section table and put it here. And I'll show you what ours is called in the corona discharge example. So let's go see how this is set up in the corona discharge example. So I'm just going to collapse everything so that we can do it from a fresh window. So if we expand the field dynamics option, I've put in 3 species. So nitrogen plus, electrons, and secondary electrons. And for the fluids option, I've put in a neutral nitrogen molecular background. So the simulation gets started with 1 free electron. And that's just, so we can see that free electron if we click on the particle loader box, the box next to particle loader, and we zoom in, and there's that electron right there. So I gave it initial energy or velocity of 0 because I'm assuming it doesn't, whatever energy we give it, it's going to gain a lot more through this potential difference. So I just set it to 0. And how did I just initialize a simulation with 1 electron? So the way I did that was in the volume. If you remember, you have to specify the volume where the particle is loaded. I used these parameters: x begin particle, x end particle, y begin, y end, z begin, z end. So if we go up and just look at 2 of those under the parameters option, and if we go to x begin particle, I started it at 0, and x end particle is x begin particle plus dx. So the electron will be initialized in just 1 cell, and that's the same with y and z as well. So y begin is, I began it just above the sphere, and then it ends where it's initialized, it ends wherever I began, plus dy. So that's how I did that. Now, there's two ways that you can load a particle. You can use grid placement and you can use bit reversed. Bit reversed is just randomly placing the particle in the cell. I chose to just place it on the grid, and this allows me to place it exactly where I want to place it. And then I just did one particle per cell. So that's how I just initialize the simulation with one particle. Now that electron, so there's two more populations here. There's N2 plus and secondary electrons. I don't start the simulation with those species. Those two species form only from reactions. So I've got this impact ionization reaction, which says N2 plus my initial electron forms N2 plus the electron that's on the left plus the secondary electron. So I get another electron from this collision. And then there's another reaction that's exactly the same, except for N2 hits the secondary, forms a nitrogen plus ion, and then it forms two secondaries. And that's how this cascading effect is launched. The cross-section table is here. I went and found an ionization cross-section table for N2, for molecular nitrogen. And I input that cross-section table here, the name of it, right here. And that cross-section table has to be in the same directory as the input file. So here's a neat little trick. If you hover over this region between this leftmost region where Analyze, Visualize, Run tabs are, and the setup tree, if you hover there, then you can pull to the right, and then you'll see all these tables that are in there. All this data sets that are in there. Of course, you would only want to open up ASCII data, because these are binary data sets. You wouldn't want to try to open those. But here's my cross-section table. So if I double-click there, and then you can see that what the cross-section is as a function of energy. So the leftmost data is a two-column data set. The left is energy of the electron, and the right is the cross-section. So you see that the cross-section is 0, and it becomes non-zero only above the ionization energy of about 15 eV. So if we scroll down, then you can see that right around 15 eV, the cross-section becomes finite. Okay, lastly, let's take a look at the boundary conditions. So I only set up one boundary condition. Remember that there is a default boundary condition, and that's absorbing. And the reason that there is a default boundary condition is because if a particle leaves the simulation domain, you'll likely get a segmentation fault, since that particle enters a portion of memory that hasn't been allocated by the simulation. So for numerical stability and you really just, if there's nothing that's set up, we want to absorb particles there. You can override that by establishing your own boundary conditions. So I did accumulate boundary. So if you right click here, then you can do add particle boundary condition. And one of those boundary conditions is called accumulate. So you can do cut cell accumulate. And that's what I did. Cut cell means it's a geometry. So I did cut cell accumulate for every single one of these populations. And I accumulate on the dielectric. So there's my dielectric. So when a particle hits a conductor, it will get absorbed and be neutralized. But when it hits a dielectric, it actually can accumulate and sit on the surface. And lastly, let me just go over a few more boundary conditions that you can add. So if we go back to vsim.sdf, and I right-click on electrons, and I hover over Add Particle Boundary Conditions, these are all the boundary conditions that you can add in the visual setup. So suppose that a particle hits a boundary and it just bounces off that boundary. It goes back into the domain, like a racquetball hitting a wall. Then you have to select what surface it'll bounce off of. So this is saying when it hits lower x, it'll bounce. And then you could add a different boundary condition. Say, so we have to add boundary conditions for any geometries. So you can do an electron cut cell, absorb, and save, and then it'll ask you to select the geometry down here. If you don't select the geometry, you'll get an error. Absorb and save means that when a particle hits that boundary, information about that particle will be saved, which you can then use in a history. And I'll show you how to set up histories in another video. But basically, when a particle hits, in this case, when a particle hits this boundary up here, this geometry, that information about that particle will be saved, such as the charge, the time that it hits, the location that it hits, the velocity and energy that it hit at, etc. So that's a very handy thing for setting up histories. Okay, so that concludes this video in which I went over how to add particles, particle boundary conditions, and reactions. In the next video, we will continue to cover the basic steps needed to set up most simulations. Thank you for watching.